Hi, welcome back to my class in number theory. For today, we will take up the Pigeonhole Principle and the Principle of Mathematical Induction. In the last lesson, we took up the well-ordering principle and some basic axioms or properties of integers. Because as we said, integers are the building blocks of theory of numbers. The Pigeonhole Principle and the Principle of Mathematical Induction together with the well-ordering principle are the three basic tools that we will use in proving some properties of integers. The three basic tools for proving some properties of integers are: number one, well-ordering principle, which we have taken last time, and it states that for any non-empty subset of the set of positive integers or the set of natural numbers, also known as the set of counting numbers or whole numbers, there is a least element for that non-empty subset of the set of natural numbers. And the second basic tool is the Pigeonhole Principle, which we will state today. And the third basic principle is the Principle of Mathematical Induction. Again, these three basic tools we will use to prove some properties of integers. We go now to the Pigeonhole Principle. The Pigeonhole Principle states that if X objects are placed in Y boxes such that X is greater than Y, then there is at least one box containing more than one object. This Pigeonhole Principle is an example of if-then statement. In the if-then statement, there is a premise, the condition given, and there is a conclusion following from the condition given. In the Pigeonhole Principle, the given are X objects and Y boxes. The number of objects is more than the number of boxes. That is, X greater than Y means the number of objects to be placed in Y boxes is greater than, more than, the number of boxes. If that is the case, then the Pigeonhole Principle concludes that there is at least one box contains more than one object. Because number of objects to be placed in the boxes is more than the number of boxes, then the Pigeonhole Principle says that there will be at least one box that will contain more than one object. And that Pigeonhole Principle is an example of if-then statement. We take a specific example. Suppose we are given 3 marbles, and these are the objects mentioned in the Pigeonhole Principle. Therefore, X in this example is 3. We have 3 objects that are 3 marbles, and these 3 marbles or 3 objects are to be placed in these boxes. And we have 2 boxes in the Pigeonhole Principle. Y is equal to 2. Y is the number of boxes, 2. X is the number of objects, 3. In this example, the 3 objects are marbles. And we have to place these, we have to put these marbles into the 2 boxes. And all of these marbles have to be placed in the 2 boxes. Because the number of objects or marbles, is greater than, more than the number of boxes. There are 3 marbles, and there are 2 boxes, so the number of marbles is 1 more than the number of boxes. And the pigeonhole principle says that if this is the case, if the number of objects is greater than the number of boxes, at least one of these 2 boxes will contain more marble. One possibility, if we place 1 marble to each of these 2 boxes, then the remaining 1 marble has to be placed in this box or in this box. Hence, if both boxes have to contain marbles, one of these 2 boxes will contain 2 marbles. Or we can place all the 3 marbles in the first box and nothing in the second box. And the conclusion is still true. One of the 2 boxes contain more than at least one or more objects. If the number of objects in this example, or the number of marbles in this example is 4, and this premise is still satisfied, the number of objects is greater than the number of boxes, and we have to place this equal number of marbles to these 2 boxes, then each of the 2 boxes will contain 2 marbles. If we are to place equal number of marbles, and that's possible because we have 4 even number of objects and we have 2 boxes, even number of boxes. And 4 is divisible by 2, that means 4 divided by 2, 2 objects can be placed in each of the 2 boxes. But if we place only one marble or object in the second box, then the first box will contain 3 marbles, because all the 4 marbles have to be placed in the 2 boxes. And if the second box will contain only 1 object or 1 marble, then the first box has to contain 3 marbles. And the conclusion is still true. At least one of the boxes will contain more than 1 object. Now, we will prove this pigeonhole principle. And the proof of this pigeonhole principle is proof by contradiction. By proof by contradiction, we will assume the opposite of the conclusion of the pigeonhole principle. The conclusion says there is at least 1 box that contains more than 1 object. And the opposite of this conclusion is that none of the boxes contains more than one object. And we will show that assumption that none of the boxes contains more than 1 object will lead to a contradiction, and we will conclude that the conclusion that there is at least 1 box containing more than 1 object must be true. We now prove the pigeonhole principle. As I said, we will prove it by contradiction. We will assume the opposite of the conclusion of the pigeonhole principle. The conclusion in the pigeonhole principle states that there is at least 1 box that contains more than 1 object, and the opposite of that is none of the object contains more than 1 object. So we assume that the opposite of that conclusion of the pigeonhole principle is true. This is the proof of the pigeonhole principle, and we will prove it by contradiction. And we suppose that none of the boxes, the number of boxes is denoted by Y. None of the Y boxes contains more than 1 object. The number of objects is denoted by X. Now, if none of the Y boxes contains more than one object, then that can happen in two ways. The number of objects is exactly equal to the number of boxes. That is, we can place exactly one object to exactly one box. And that is one possibility where this can happen. None of the boxes contains more than one object. When the number of objects is equal to the number of boxes, then each box will contain exactly one object, and none of the boxes will contain more than one object. So we write then this assumption, the opposite of the conclusion of the pigeonhole principle, leads to the statement x is equal to y. If this is true, then we say that the number of objects is equal to the number of boxes. And in this case, if none of the boxes will contain more than one object, exactly one object will be placed in one box because the number of objects is equal to the number of boxes. And that's just one possibility where none of the boxes contains more than one object. The other possibility is that some of the Y boxes contains exactly one object, and the other boxes contains none of the object. That is, exactly one object is placed in some of the boxes, and no object is placed in the other boxes. And that can happen when the number of boxes is, if the number of object is less than the number of boxes. In symbols, we write x is less than y. Again, this statement supposes that none of the boxes Y contains more than one object. This statement is the opposite of the conclusion of the pigeonhole principle that says if the number of objects is greater than the number of boxes, then there is at least one box that contains more than one object. And we will show that this statement, the opposite of the conclusion of the pigeonhole principle, will lead to a contradiction. And this statement, none of the boxes contains more than one object, can happen in two ways. The first possibility that none of the object contains more than one object is that the number of objects is equal to the number of boxes. And because none of the boxes contains more than one object, if the number of objects is equal to the number of boxes, we can place exactly one object to exactly one box. One box will contain exactly one object. Or there are Y boxes, some of the boxes contains exactly one object and the other boxes are empty. And this statement is also true. None of the boxes contains more than one object. If the number of objects is less than the number of boxes, we can place one object to some of the boxes, and some of the boxes are empty because the number of objects is less than the number of boxes. And none of the boxes contains more than one object. But consider this 2x equals y. The number of objects is equal to the number of boxes, or the number of objects is less than the number of boxes. These two are contradiction of the premise of the pigeonhole principle. The premise of the pigeonhole principle says that if X objects are placed in Y boxes, X objects are placed in Y boxes such that X is greater than Y. This is the premise. The number of objects is more than the number of boxes. And if the number of objects are placed in, if X objects are placed in Y boxes such that the number of objects is more than greater than the number of boxes, then there is at least one box, or one or more boxes contains more than one object. But if we now see that if none of the boxes contains more than one object, then this can happen only when the number of objects is equal to the number of boxes, or when the number of objects is less than the number of boxes. And these two contradict this premise of the Pigeonhole Principle, that the number of objects is greater than the number of boxes. Thus, this statement that none of the boxes contains more than one object is a contradiction of the premise or the given condition of the Pigeonhole Principle that says the number of objects is greater than or more than the number of boxes. So we write the sentence, as we said, this possibility x equals y or x less than y for none of the boxes to contain more than one object contradict the premise or the given in the Pigeonhole Principle that the number of objects is greater than the number of boxes. X equals y is definitely a contradiction of x greater than y, and also x less than y is a contradiction of the given that the number of objects x is greater than more than the number of boxes y. Therefore, if this assumption or statement leads to a contradiction, then the conclusion of the Pigeonhole Principle must be true, that at least one of the boxes contains more than one object if the number of objects is more than the number of boxes. And this completes the proof of the Pigeonhole Principle, the proof by contradiction. The shaded box is placed at the end of proof to indicate that the proof is completed. Now we will state the principle of mathematical induction. We now state the third of the three basic tools for proving properties of integers. The first two being the well-ordering principle. The second we have just taken is the Pigeonhole Principle, and the third is the principle of mathematical induction. we state the principle of mathematical induction. Principle of mathematical induction. Let P of n be a statement concerning integer variable n. P of n here can be a mathematical statement, is a mathematical statement usually. It can be in the form of formula, in the form of equation, and the variable n here will take only values that are integers. We continue, let n sub 0 be specified integer n. N is assigned a specific value, n sub o, and n sub o is an integer. The statement P of n is true. This is we read this as for every. This symbol is used to represent for every. We read the statement P of n is true for every integer n if the following can be established. Now, if there is a given statement concerning integers and you want to prove that this statement in the form of an equation or formula where the variable n is an integer is true for every integer n, then these two must be shown to be true. The first one that you have to show is that the statement P of n is true for the specified value of an integer, of the integer variable n. You assign a specific value for you assign a specific value n sub o for the integer variable n. Now, the integers, the set of integers include the set of negative integers, the 0, and the positive integers. If you want to show that the given statement P of n is true for the set of natural numbers or the set of positive integers, then we usually take n sub o as 1 because 1 is the smallest positive integer or the least element of the set of natural numbers. For the set of natural numbers, we usually take n sub o equals 1. So in the first step, we will show that P of n is true for n equals 1. If n is the integer variable that takes values in the set of natural numbers, denoted by capital N, the set of natural numbers denoted by capital N, and its elements are the set of positive integers or the set of counting numbers or the set of whole numbers, and its smallest element is 1, positive 1. And the second one that you have to prove is P of n, the statement P of n is true for n equals k plus 1, where n is greater than the specified value of specific integer n sub 0, but less than equal to k, whenever P of n is true for n equals k. Now, to establish letter B, we assume that the statement P of n is true for an integer k. And whenever the statement P of n is true for n equals k, then we must show that the statement P of n is also true for the integer k plus 1. And if you can establish A and B, then we conclude at the end that the statement P of n concerning integer variable n must be true for all integers. Now, we take an example for applying this principle of mathematical induction. Consider the following example. Show that for every n is an integer variable, n is an element of capital N. So, the values of the integer variable n are natural numbers or positive integers or counting numbers from 1, 2, 3 up to positive infinity. And for every natural number and element of n. We want to show that summation of I, where I is 1 to n, is equal to n, the upper index of the summation. I is the lower index, I equals 1 is the lower index of the summation, n is the upper index of the summation. And the summation of I for I is 1 to n. This represents the sum of the first n integers. And this sum is simply equal to n multiplied by quantity n plus 1 all over 2. Suppose n here is 50 or 100. The left-hand side would be summation of I equals 1 to 100. That is, you will add the numbers from 1 to 100, or 1 plus 2 plus 3 plus 4 plus up to plus 100. But instead of performing that long addition, the sum of the integers from 1 to 100 can be obtained by performing this. Multiply n by n plus 1 and divide by 2, where n in our example is 100. Just for example, n is 100. The sum of the integers from 1 to 100 is equal to n 100 multiplied by 100 plus 1. Divide by 2. And 100 divided by 2 is 50. And 100 plus 1 is 101. And we multiply 101 by 50. One hundred one multiplied by 50 is 5,050. So this is like a formula for getting the sum of the first n integers. Instead of adding the integers from 1 to n, you can get the sum of the first n integers, the integers from 1 to n, by using this formula, n multiplied by n plus 1 divided by 2. Like in this example, if n is 100, that means you will get the left-hand side means that you will get the sum of the integers from 1 to 100. You will add 1 plus 2 plus 3 up to plus 100. But instead of doing that addition, you can get the sum of the integers from 1 to 100 by multiplying n by n plus 1 and divide by 2. Where n is 100, multiplied by n plus 1, n is 100. And we divide the product by 2. I divided 100 by 2. We have 50 multiplied by 100 plus 1 is 101. And I multiplied 100 by 50. The product is 5,050. 5,050 is the sum of the first 100 integers, 1, 2, up to 100. Now we will prove by using the principle of mathematical induction that this formula is true for every natural number n. This formula is now the P of n in this statement of the principle of mathematical induction. P of n is a statement concerning integers. And in this example, the integers are specifically the positive integers or the natural numbers. And we will now prove this by using the mathematical induction. And our proof will consist of two parts. The first part, we will show that this is true for n equals n sub 0, where n sub 0 is a given specific integer, because our set is the set of natural numbers. We assign 1, n equals 1 for letter A, or because 1 is the smallest natural number or the smallest positive integer. And the second part of the proof, we will assume that this uh, equation or formula is true for an integer or natural number k. And if that is true, we have to prove that this statement is also true for an integer or natural number k plus 1. Again, I will state specifically what we have to show in our proof. To prove that summation of I is 1 to n equals n times quantity n plus 1 divided by 2 for every natural number n, we show these two. According to the principle of mathematical induction, letter A, we must show that summation of I is 1 to n equals n times quantity n plus 1 over 2 is true. This equation or formula or statement is satisfied for n equals 1. Now, the specified value of n is 1, and we take 1 as the specific value of n since our integer variable takes values in the set of natural numbers or the set of positive integers, where the smallest element or the least element of the set of natural numbers is 1. And the second one we have to prove is, we must prove that summation of I is 1 to n, equals n times quantity n plus 1 over 2, or we must show that this statement is true for n equals k plus 1. Given that, or whenever that the statement is true for n equals k, in letter B, we take this statement to be true for n equals k. That is, if n equals k, replace n with k. You get summation of I, where I is 1 to k, is equal to k, n is k times quantity k plus 1 all over 2. Or this statement we take as true. If this is true, that summation of I is 1 to k is equal to k times quantity k plus 1 divided by 2 is true, then we must prove that this statement, given statement, summation of I is 1 to n equals n times quantity n plus 1 all over 2 is also true for n equals k plus 1. And in that proof, we will use this statement or this equation which we take to be true. So we now proceed with the proof, with the first part of the proof by mathematical induction. We take n equals 1. For n equals 1, we must show that this equation or statement is satisfied, is true. We start from the left-hand side. We have summation of I, where I is 1 to n, but n is 1. So I is 1 to 1. And this summation of I, where I is 1 to 1, will consist of only one single term, 1. And so the value of the left-hand side is 1. We compute the value of the right-hand side. N times quantity n plus 1 all over 2, where n equals 1. We have n times quantity n plus 1 over 2. If n is 1, we have 1 times quantity n is 1 plus 1 over 2. We have 1 multiplied by 1 plus 1 is 2, and divide by 2. And 2 will cancel out because 2 over 2 is 1. And what remains is 1. So the left-hand side of this statement or equation is 1. And the right-hand side of this statement or equation we have shown is also 1. So this equation is true. the equality is maintained. The equality is true. The equality between this and the right hand side is true for n equals 1. Therefore, we conclude for letter A that summation of I we therefore conclude that in part A of the proof, first part of the proof, the summation of I for I is 1 to n is equal to n times quantity n plus 1 divided by 2 is true. This statement is true for n equals 1. As we have shown, the value of the left side is 1, the value of the right hand side is 1. So this statement is true for n equals 1. And that's the first part of the proof by mathematical induction. Now we proceed with the second part of the proof. In the second part of the proof, we take this statement, given statement or given equation to be true for n equals k. That is summation of I when n equals k. You get summation of I for I is 1 to k, n is k, equals n is k, k times quantity n is k, k plus 1 divided by 2. We take this to be true. And we will use this to show that this is statement summation of I where I is 1 to n equals n times quantity n plus 1 divided by 2 is also true for n equals k plus 1. We start from the left hand side. We have summation of I is 1 to n now is k plus 1. From the left hand side, we have summation of I is 1 to n. And in letter B, we take n equals k plus 1. And we expand this summation. The summation of I for I equals 1 to k plus 1 means the sum of the integers from 1 up to k plus 1. So the expansion of this is if we write the expansion of the summation of I for I is 1 to k plus 1, it's equal to the sum of the integers 1, 2, 3 plus up to the last integer k plus 1. The integer before k plus 1 is k. You notice that the integer preceding an integer, the integer preceding 3 is 2, and 2 is always less than 1 than 3. So the integer preceding k plus 1 is an integer that is 1 less than k plus 1. And that is k. But the summation from 1 to k, this sum, using sigma notation or compact notation is equal to summation of I where I is 1 to k plus k plus 1. Again, we write the sum 1 plus 2 plus 3 plus up to k in compact notation using sigma notation, and it is equal to summation of I where I is 1 to k plus the last term k plus 1. But this summation of I for I is 1 to k, we take as equal to k times k plus 1 over 2. And this is equal to k times quantity k plus 1 equals 2 because we take this statement or this equation as true. So the summation of I for I is 1 to k is equal to k times quantity k plus 1 divided by 2 plus k plus 1. And we combine these two terms. If you write the denominator of k plus 1, the denominator is 1. And LCD of 2 and 1 is the lowest common denominator. The lowest number that can be divided by 2 and 1 is 2. And that's the LCD of 1 and 2. And we find the numerator of the combined. We have 2. Divide the LCD by its denominator and multiply the quotient by the numerator. We have 2 divided by 2 is 1. 1 multiplied by k plus 1 equals k times k plus 1. Plus, again, divide the LCD, lowest common denominator, by the denominator of the second term and multiply the result by the numerator. 2 divided by 1 is 2 multiplied by the numerator k plus 1. And by inspection of the numerator, you can see that the first term and the second term have a common factor, and that common factor is k plus 1. So we factor out k plus 1. We factor out k plus 1 from the first term, and what is left in the first term is k. Plus, factor out k plus 1 from the second term, and you are left with 2 in the second term. All over 2. Hence, the summation of I, where I is 1 to k plus 1 is equal to k plus 1 times quantity k plus 2 all over 2. And we have to show that this is equal to n times n plus 1 divided by 2 if n is replaced with k plus 1. If the value of this left-hand side is equal to the value of the right-hand side, then we conclude that this statement or equation is true for n equals k plus 1. And we are done with the proof. On the other hand, we compute n times quantity n plus 1 divided by 2 for n equals k plus 1. N is k plus 1. We have k plus 1. Multiply by quantity n plus 1 where n is k plus 1. K plus 1 plus 1. All over 2. We simplify the right-hand side. We have k plus 1. Multiply by k. 1 plus 1 is 2. All over 2. Thus, the summation of I for I is 1 to n. And n equals k plus 1, which has this value, is equal to the value of n times n plus 1 over 2, which is also equal to k plus 1 times k plus 2 all over 2. Hence, we conclude that this equation or statement, mathematical statement, is true for every integer, for every natural number n. And we write now the conclusion. Thus, in the second part of the proof by mathematical induction, we have shown that summation of I, where I is 1 to n, is equal to n times quantity n plus 1 divided by 2 is true for n equals k plus 1. Because we have shown that summation of for I is 1 to n and n equals k plus 1 has a value of quantity k plus 1 multiplied by quantity k plus 2 all over 2. And this right hand side n times n plus 1 all over 2 for n equals k plus 1 we have shown is also equal to quantity k plus 1 times quantity k plus 2 all over 2. Therefore, if for every natural number n equals k, the statement is true, we have shown that for the integer k plus 1, the given statement or equation is also true. Therefore, in general, we conclude that for every natural number small n element of the set of natural numbers, the summation of I for I is 1 to n is equal to n times quantity n plus 1 all over 2. This is 2. Again, in general, we conclude that the summation of I for I is 1 to n equals n times quantity n plus 1 all over 2. And this statement is true for every natural number or positive integer element of the set n of natural numbers or positive integers. Now, for your practice, please try the following. Prove the following by using mathematical induction. Show that for every n element of n, the set of natural numbers or positive integers, summation of I squared for I is 1 to n. This is the sum of the squares of the integers from 1 to n. And this summation is equal to n times quantity n plus 1 times quantity 2n plus 1 all over 6. Example, n is 3. Then for the left hand side, you will have summation of I squared for I is 1 to 3. And it is equal, the summation of I squared for I is 1 to 3 is equal to the sum of the square of 1 plus next to 1 is 2, the square of 2, plus next to 2 is 3, the square of 3, plus the square of 3. And you get 1 plus the square of 2 is 4, plus the square of 3 is 9, or 14. But instead of performing this long addition and getting the square of each integer and adding the squares, you may compute the sum of the squares of the first n integers, the integers 1 to n, by computing n times n plus 1 times quantity n plus 1, quantity 2 n plus 1 all over 6. Let us check if 14 is correct for n equals 3. For n equals 3, we get 3 multiplied by 3 plus 1 is 4. Multiplied by 2n, n is 3, 6, 2 by 3, 6 plus 1 is 7. And divide by 6. And 3 and 6 is both divisible by 3, we divide by 3, we get 2. 4 is divisible by 2, and it's 2. And 2 by 7 is 14. Thus, for n equals 3, this is a specific value of n, a natural number or positive integer. We have shown that summation of I squared for I is 1 to 3 is equal to n times n plus 1 times quantity 2n plus 1 divided by 6, where n equals 3. But you will show by using the principle of mathematical induction that this statement is true for every n element of the set of natural numbers, and your proof must consist of two parts, A and B, as we have shown in our example for today. And in the next lesson, we will have more examples for using the principle of mathematical induction to prove other properties of integers. If you have question about the lesson today, you ask your question in the comments below. And don't forget to subscribe to my YouTube channel, Art Kalison, or ask your friends and classmates to subscribe to my YouTube channel, Art Kalison, the channel of learning and pleasure. Thank you for joining me in my class today.